Today we're going to be delving into the specific components of a C++ program, and we'll be continuing to do that with the next lecture as well. So the three basic components we'll be going over today are variables and data types, assignment statements, and arithmetic expressions. Next time we'll talk more about arithmetic expressions, also go into input, output, and into comments. So I just want to quickly review what a C++ program looks like. So we're going to have as our problem description that we want to compute the amount of change we have in our pocket, and that's going to be based on the number of nickels, dimes, and quarters we have. So as an example, if I have 3 nickels, 4 dimes, and 6 quarters in my pocket, I would have 205 cents. And if you do the math, you would multiply the 3 nickels by 5 cents, the 4 dimes by 10 cents, the 6 quarters by 25 cents, and you would get the arithmetic you see there, and hopefully you too will arrive at 205 cents. So basically we need to implement this problem as a program. Remember last time we talked about how you might do this as specifying the inputs and outputs and then a short algorithm. Well, the inputs should clearly be the number of nickels, the number of dimes, the number of quarters. The output is the number of cents, and the calculation is kind of embodied right here. It's going to be the number of nickels times 5 plus the number of dimes times 10 plus the number of quarters times 25. So here's the program with some of this scaffolding stripped away, like the main and the include statements. So we start with the variable declarations. If you remember, variables are named memory locations. So we have 3 variables to store the number of nickels, dimes, and quarters. And then we also declare a variable called cents that's going to store our calculated result of how many cents are in our pocket. Then we need to get input from the user, specifically the number of quarters, dimes, and nickels in their pockets. So remember that cout is saying we want to output something to the console, and specifically we're outputting the string, please enter the number of quarters, dimes, and nickels in your pocket. Then we want to read that input, so the cin says we're going to read the input from console in. The greater than says that we're performing an input operation, so we're reading the first piece of information and placing it into the memory location labeled quarters. The next one goes into dimes. The third one is stored in nickels. And then after we've done our computation, we'll get to that in a moment, we want to output our result, and we do that by again outputting to console and outputting the string cents equal and the value that is stored in the variable cents, and then a new line character. Last time you saw it as endl. This is a second way to do it, so just like English has some synonyms, so does C++, so 2 different ways to specify an end line. And finally, assignment and arithmetic. So the arithmetic is right here. This is the computation for the number or amount of change in your pocket. We evaluate this right-hand side expression, and we assign the result to cents. That is, we store the value in cents. So if I entered, for example, 3 for nickels, and I entered 4 for dimes and 6 for quarters, then based on what we had before, cents would end up with the value 205. And I like to often think of variables this way as like a box, a labeled box with a value in it. So you'll often see me draw a labeled box, and basically I'm saying that the contents of that box represents the variable's value. Okay, so we're going to start today by talking about variables and data types. And A variable, as I said last time, is a named memory location that stores a value. So here, where I said int nickels, the compiler is going to create a named memory location for me called nickels. And you, again, think of it as a box, and I can put a value there. But in this case, I haven't specified any initial value, so I put a question mark there to denote that the value is undefined. There is some value there. It's left over from another program, but we have no idea what that value might be, hence the question mark. And variable declarations start with a type such as int or double, and that's because every variable can store only a single type of value. C++ is very picky, so we will see that a number of types include integers, which is how I declared nickels here, real numbers, which is how I declared dollars, but instead of real, C++ has a number of data types. You'll see that in a moment. So here I said it was what we call a double. Later on, we'll be introducing additional data types like strings, but that's for later. The syntax, as you can see here, variable declarations start with some type, and then the name of a variable, and finally the semicolon. Again, very important to include that, because without it, in effect, you have a run-on sentence in C++, just like if you omit a period at the end of a sentence. In English, you have a run-on sentence, and the compiler will complain. You're also allowed to have a comma-separated list of names after your type specification. So here we have a comma-separated list, nickels, dimes, and quarters. And just like in a good English composition, you tend to group things into sections. We like to do that in computer programs as well. There's some things that are required and others that are optional. Where we place the variable declarations is somewhat optional. We do have to declare a variable before we use it. So by convention, we group the variables all together right after main and before we start executing any statement. So here you see right after main, but before any of the statements where we're asking the user for input or where we're trying to do some kind of arithmetic computation. Okay, so the big thing about variables, they're very important. We often store values into them, and we want to read values from them. If you're familiar with a calculator, you would often do like store 1 to store into register 1 or store 2 to store into register 2. Same thing, we want to be able to store values into our variables. There's 3 ways you can do it. First of all, when you declare the variable, you're allowed to provide an initial value. So here we're saying that the initial value for age is 300. And if you remember from the previous slide, you're also allowed to declare a variable without an initial value, and in that case we put a question mark next to the variable to indicate we don't know what its current value is. Once you've declared a variable, regardless of whether or not you've initialized it, there's 2 basic ways to assign values, new values to it. One is using something called an assignment statement. And that simply takes the value on the right-hand side of the equal sign and places it at the memory location specified on the left-hand side. So in this case, we're saying that we want to assign the value 42 to the variable called number. So that means we'll scratch out the question mark because we're now putting 42 into number. The other way that we can assign a value is through an input statement. And in this case, we're reading from the console. The user provides some value. Let's say the user inputs 60. So what would happen is that, again, I'll just delete it there. It would become 60. So as you can see, the old value is always replaced by the new value, and the old value is lost. And then here's another assignment statement. So the 60 now would be lost, and what we would end up putting into number would be 55. So again, 3 ways to place values into variables. Right when you declare the variable, you're allowed to provide an initial value. Thereafter, you can use either an assignment statement or an input statement to assign values to a variable. There's some naming conventions with variables that you'll need to remember, so this is a good slide. First of all, you need to start your variables with a letter or an underscore, and your variable names are allowed to contain letters, digits, and underscores. You're not allowed to use blanks, commas, or special characters like question marks, hash marks, commas, periods. You supposedly have an unlimited size. You don't want to make them ridiculously long. There used to be a limit of 31 characters in the old days. I'd say that's a good limit. Try to make your variable names meaningful because it makes your code a lot more readable. Finally, variables can't be C++ keywords. So for example, you can't choose main. You're not allowed to choose include. You're not allowed to choose using. Those are C++ keywords that you're not supposed to be naming your variables after. And if you do, the compiler will complain. So if we just look here, some valid ones, all of these right here are valid. They all start with a letter. They contain only letters, numbers, or the underscore character. In contrast, these identifiers are not valid. If you think about it for a moment, Starbucks is no good because it doesn't start with a letter, and actually star is also not an allowable character. 4 aces is no good because it starts with a number and it has to start with a letter. A to Z is no good because dashes aren't allowed. So you'll remember that we said that we had to declare every variable to store a specific type of value. C++ is very strict about it. And initially we have 2 main types of values, the kind that you're really familiar with in everyday life, which are numbers and strings of characters. So, and then in real life that you can have integers and you can have real numbers. So that's what C++ does. In effect, I'll have a little taxonomy here. So a number can be either an integer or it can be a real number, but we don't declare anything as real. In fact, you'll see the book says a real number can be declared as either a double or as a float. And either one is fine. I prefer you declare your real numbers as doubles. All it really means intuitively is there's double the precision. So a computer cannot store an infinite number of decimal digits. Theoretically, a real number could have an infinite number of decimal digits, like pi, or if you do 1 divided by 7, the result is an infinite sequence. You can't store an infinite sequence of digits with a computer. There's a limit on it. Basically, a double just says we can store about twice as many digits with a double as we could with a float. So bigger numbers can be stored with doubles. That's why I like them. And then we're also going to have strings. We're not yet telling you how to declare a variable that can store a string, but for output, we often are wanting to print strings to the console. So strings are simply any sequence of characters. They could be numbers, they could be punctuation mark, pretty much anything that you might put into a report, an English essay, can go between those quotes. And that's how C++ knows that you intend to use a string, is it starts with a double quote and it ends with a double quote. Now, one thing you're going to find yourself running into periodically is wanting to assign integers to variables that are declared to hold real numbers, or you're going to want to assign a real number to a variable declared to hold an integer. And it's very easy to assign an integer to a variable that's declared to hold a double, because basically C++ just converts that integer to a decimal number. So basically that's what gets stored into dollars. It's a little trickier when you want to assign a real number to an integer variable. And the reason is that you're going to lose precision. An integer variable cannot, under any circumstance, store a real number. So what happens is that the compiler truncates the 0.51 and just leaves the integer. It does not round. It truncates the decimal places and just stores the integer into average. Now, our C++ compiler does this without warning you. Other C++ compilers will complain about what they call a loss of precision because before it was really 3.5, but you're storing it as 3. Okay, so that takes care of variables and declarations. We now want to talk about how you can assign values to variables using assignment statements. So you've seen that syntax already where you have a right-hand side expression and that expression gets evaluated and assigned to a variable on the left-hand side. And you can either have an arithmetic expression as I have here, or it could be a simple value like 0 as I have there. And the basic syntax for an assignment statement is you have a variable on the left-hand side. It always has to be a single variable, no exceptions, then the equal sign, and finally some expression or a value on the right-hand side. And what happens is the order of evaluation is C++ evaluates the right-hand side expression. I'll abbreviate right-hand side as RHS expression to produce a value. And then 2, it assigns that value or stores that value into the variable on the left-hand side. And I'll abbreviate left-hand side as LHS. So this allows us to do some wonderful and marvelous things that are going to look kind of strange to you if you're a math-oriented type of person. So it means that statements like count equal count plus 1, which are an absolute mathematical dribble, nonsense, they actually make sense in a computer program. Remember what I said about how this statement will be executed. Let's say count currently has the value 2. Well, apply the 2 rules. Rule 1 is to evaluate the right-hand side expression. So the count, the value is 2. We add 1 to it, we get a value of 3. So 2 plus 1 is 3. That value is now assigned to count. So count ends up incremented by 1. It's a very handy idiom which we use all the time in computer science. Okay, so we're going to wrap up the lecture by just briefly talking about arithmetic operators. We'll get into them in more detail next time. So we have the 4 basic arithmetic operations that you're familiar with in C++: addition, subtraction, multiplication, and division. We also have a new operation which you may not have seen before, the remainder operation, which is represented with a percent sign. And it's also called the mod operator. And what it does is it returns the remainder of an integer division. So if you divided 5 by 3, you would get a quotient, which is 1. I represent the quotient as Q. You would get a remainder, which is 2. So 5 mod 3, 5% sign 3, is going to return the value 2. And this operation is only valid with integer operands because it does integer arithmetic. So you might look at this and think, oh, well, the remainder is a quotient of 1 and a remainder of 2.6. So yes, the operation does make sense, but it's illegal in C++. Only integer division supported with the remainder operation. And you might wonder, well, why even use this? Well, you actually use this a fair amount each day. Think of a clock, okay, that goes from 0 to 12. Well, how many hours in the day are there? So I'll just draw a clock. Okay, how many hours in the day? There's 24 hours in a day, right? But we don't normally say 17 o'clock. Now, I know that in the military they do, and it disambiguates. But what do we say? We say 5 p.m. Okay? How do we translate 17 to 5 p.m.? Well, in essence, what we're really doing is we're modding 17 by 12. That is, when the clock has gone all the way around to 12, it now resets and starts back at 1 again, right? So 2, 3, 4, 5. So 17 is in effect once around, which is 12 plus 5 more. So 17 mod 12 gives us 5 p.m. So you actually use this remainder operator each day with time, although you may not realize it. And we do this a lot in computer science to also kind of allow things to wrap around. So you also probably are used to using parentheses to group operations in arithmetic expressions. If you were trying to take the average of these three numbers and divide it by 3, looking at this right now, you probably think this looks a little funny, or I hope you think it looks a little funny, because when you're taught this by your math teacher, it's typically the case that division has a greater precedence or priority than addition. And hence, the division is going to get performed first, and it's going to get performed on the two operands closest to it. So while we think this, we want to take the average of 10, 30, and 50, which is 30, because 10 plus 30 plus 50 is 90, divided by 3 is 30. What we're really going to get here is the computer is going to evaluate it as 10 plus 30 plus, now it's going to divide 50 by 3, and because it's going to do integer arithmetic, both operands are integers, so it does integer arithmetic, it gets 16. And now it adds them together and gets 56, which isn't what we intended. So to fix that problem, you can always group your operations using parentheses, and that way those operators get evaluated first. So in this case, the parenthesized expression is evaluated first. It evaluates to 90. We now divide that by 3, and it gives the result we thought it would, which is 30. So the order in which a computer, or actually a calculator for that matter, evaluates arithmetic expressions is very well determined. It first evaluates parenthesized expressions. Those have the highest precedence. Next, it evaluates multiplication, division, and the remainder operations. And the lowest precedence is given to the addition and subtraction operators. And then if you have two operators at the same, in the same expression, let's say here I had 3 times 6 divided by 2, then we evaluate those operators left to right. So in this case, the times gets evaluated first, so it's gets the two operands 3 and 6, so that evaluates to 18, and then we divide it by 2 to get 9. So let's just apply those rules to these two arithmetic expressions, which you'll note they both have the same numbers, but one is parenthesized and one isn't. So let's just see how a computer evaluates it. Remember, let's do the first or top expression first, and it's going to give precedence to the multiplication and division, and it's going to evaluate the multiplication first. So it's going to be 1 plus 2 times 3, so that's 6, plus 4 divided by 5.0. So I'm just doing it one at a time so you see the order in which the computer is doing it. So now it does the division next and gets 0.8. The reason we get now a real numbers because one of the two operands is a real number. Now we only have plus operators left, so we're going to evaluate them from left to right. So 1 plus 6 is 7. And finally, we've got 1 left, and we end up with 7.8 as our answer. Okay, so let's see how that is going to differ from this one right here. I'll come over here and evaluate it here. So the parenthesized expressions change everything. They're going to get evaluated first, and again, they'll get evaluated in left to right order. So that means that we first evaluate the 1 plus 2 and get 3. So we now have 3 times the parenthesized expression 3 plus 4 divided by 5.0. Now the one remaining parenthesized expression has precedence, so we evaluate it to get 7. Okay, and now don't get head faked. We have 2 equal precedence operators left, the times and the division. So we perform the times first because it's leftmost. So 3 times 7 is 21. And finally, we do the division to get 4.2. And if you look at the final results of the 2 expressions, they're quite different. So that should convince you that the order in which we evaluate the expressions or the operators is going to have a big effect on the value that gets computed. So we'll pick this up next time with some more examples with operator precedence, and also how we deal with mixed arithmetic, like right here where we had 4 divided by 5.0. That was an integer divided by a real number. And also, if you ever have a question about operator precedence, which you probably won't in this class, this is a good link for looking at it.